Welcome to Data Architecture Elevator podcast. Created by Agile Lab, we will explore the dynamic intersection of technology, innovation, and practices in the data space. Our company purpose is to elevate the data management game of companies that want to be data-driven, and this is the goal of this podcast too. For more information and insights, visit our website at www.agilelab.it. Feel free to reach out our architects on LinkedIn with your question. But now, let's step into the elevator with Agile Lab Data Architects. Hello and welcome to the second episode of the Data Architecture Elevator series. This second episode will focus on streaming. That is a very hot topic for data architecture. We know streaming and data in motion has been in a long evolution since 2015 when Spark Streaming came into the picture of data management, and then since that moment evolved a lot. And streaming can support a lot of use cases in data analytics, and today we will deep dive on them. Today with me we have Andrea Fonti.
Hello.
Andrea Novara.
Hello everyone.
And Antonio Murgia.
Hi everyone. Thanks for having me.
Good. So we know streaming can be applied on both operational and analytical use cases. It's a very different environment where you can apply this methodology to process the data in real time. But the goal it's always the same. So process the data in the fastest way possible to short the time to insight for the end user or for other applications. So maybe we can start by introducing a couple of use cases that you work on, so we can set the right context for the further discussion. Maybe Antonio, do you want to tell us briefly the experience that you had in the past with streaming?
Yeah, sure. So probably my biggest experience with the streaming technologies was, let's say, platform to process incoming data from IoT devices. To be more specific, it was devices that track the vehicles moving on the road, insurance black box, that's how we usually call them. They were metering different measures like speed, position, tank fuel level, and use RPM, and this kind of stuff. And so that kind of platform was, I think, in the middle between an operational and analytical one, because definitely it was mission critical. Definitely we had very severe SLAs, because we had to deliver our processed measures by 1 minute for all the platform, which was quite challenging. And so I wouldn't place that into a purely analytical use case and platform. The technological stack at that time, so it's not a very new technological stack, but it served very well. Its purpose was on top of Kafka, Spark Streaming, and HBase. Mainly these were the three tools, and I think it was a nice blend because Spark is quite high level, so allowed to express quite complex logic without too much effort. The downside, it's the operational side is quite complex in that case, and the whole platform actually delivered the messages on time. That what we care the most, and was also able to stay in the same technology stack and perform analytics which were, let's say, less latency sensible. So latency wasn't the first problem to address. Staying in the same technological stack helped a lot the development team, obviously, because they didn't have to switch between different technologies.
If I remember correctly, it was processing something like 100k events per second. So it was quite massive throughput to process in real time. Is it right?
Yeah, that's right. We had, I guess, around a couple of millions devices. And at peak time, so during the morning and late noon, there were a lot of messages coming every second, because those black boxes were sampling every second. So when you have 1 million vehicles on the road, you have 1 million messages per second. So, well, not everyone was on the road at the same time, but yeah, the scale was pretty huge.
Yeah. And Andrea Fonti, instead, you are the master of mainframe offloading. Tell us something about your use cases.
Yeah, mainframe offloading is mostly an operational load. So we are trying to extract data from mainframes and ingesting data on other system, let me say, creating read replicas of what is available on the mainframe. And the goal is having less load on mainframe systems that are centralized systems. So to distribute read load among different systems. It's mostly operational, since we are not doing usually analytics, but creating views of data that is available on the mainframe. Mainframes are used in the banking sector as the transactional center of everything that happens. So there is a notion of truth, what is currently the truth about a banking customer. And this is something that is a bit difficult to do, since when in the analytics space you can bear with eventual consistency. Usually on operational load, eventual consistency is not so great for data consumers. And one of the challenges in the operational sector is exactly that, maintaining transactional consistencies across different read replicas. And also there's a lot of monitoring, a lot of tracing. So let me say, well, Antonio described a use case where you receive a lot of data and you have to be fast. Here we have to be fast and also to be extremely correct. So usually our notion of fast in the operational landscape is a bit less fast, let me say, a bit slower, but more correct. So we need to have tracing, monitoring, a lot of non-functional requirements around what we develop.
Typically, the end-to-end replication from mainframe to other replicas should stay within 2-3 seconds, right? So the service level agreement of the replication, it's
usually the service level agreement is around that, and you have a lot of systems in between. So you need also to capture changes from the original database. You have a lot of ops, a lot of transformation, and the latency budget is not so much. for each hop.
Good. Andrea Novara, instead, what about your streaming experiences?
I can bring this experience from previous engagement about building a network intelligence platform for covering the infrastructure of a wireless fixed internet provider. And here the goal was to keep everything under control. They had a distributed network based on base station that was relying internet traffic, and so they asked to create an infrastructure to collect metrics about radio appliances and about the routing layer behind radio appliances, and also to collect information from the syslog infrastructure, so about the events happening on all the operating systems that were operating all the routers. And we created this integration by collecting different type of sources on a central Kafka infrastructure and processing both in terms of analytical KPI calculation, so stateful streaming, and also delivering all the events to a rule processor based on rules, which is an open source project, to identify common patterns, to understand if problems from specific appliances are related to that appliance, or let's say describe a bigger pattern. So you have an outage on a section of the network. And also to do some preemptive maintenance, because when some specific metrics are out of their usual thresholds, perhaps we'll have an outage in an appliance very soon. And the biggest difficulty was to organize all data across topics. We had problems in the skew of the data distribution across topic partitions. We identified that we had to change some configuration about the keys to even the load on specific partitions, and so on specific brokers of the Kafka cluster, and also on specific consumers, and to understand how we could describe the patterns in the root processing engine at the end of the chain, and also in the interface that presented data to the network operations center to make them more effective in fixing the problems. So we created a solution that also involved taking a log of the operations and making the network operations center people interact with each other and being able to take care of specific use cases. So it was a very complex design that also blended into the end, the management of the problems in the log.
Cool. In the past 10 years, recurrently, I heard people and vendors claiming that basically with streaming processing, you can do whatever kind of use case, and probably in the future, everything will be based on streaming systems. I have seen recently also talking about streaming data products, streaming data mesh. Antonio, what is your opinion on this? So every kind of use case can be turned into a streaming application or not? Is it efficient or not?
It might be efficient. So theoretically, it can be efficient, but it's hard to make it efficient. And the reason why it's hard to make it efficient is that streaming means it's unbounded, so theoretically infinite. And modeling and dealing with infinite data streams is not as easy as dealing with the finite ones. So the batch workloads usually, not usually, every time they are finite, the data set has a row count or whatever metric, which is fixed, while for streaming it's not. This poses a lot of complexity into the implementation of the workloads. I think the first step to make streaming main a main way of processing data is first moving to incrementality. So for now, batch workloads, most of them are not incremental. They are like full export, full reconstruction, full recalculation, full reaggregation of finite data sets, which is impossible in streaming. So it's not possible to apply the same methodology in streaming. If we move also batch workloads to that kind of methodology, which is incrementality, I think then the transition to streaming will be easier and possible at some time, at some point in time. I think one of the problems also is that streaming data mostly is time series. There is always the notion of time. And I was reading a paper yesterday from Conviva, which is a company that deals with this kind of problem. Is building a platform for time series analytics. And they state that the problem is that current languages, meaning SQL or SQL dialects that deal with the streaming data, or even the Spark data frame API, are too low level for complex event processing. And that's why complex event processing is complex to implement, and therefore incrementality, it's harder to implement. So probably we need a step up also in that direction. It's not only the tools, but even the way we express this kind of computation that needs to evolve to have a larger adoption. And on the other side, apart from the implementation cost, it's also the fact that these kind of solutions are not as battle tested as batch ones. So definitely you need to invest more on the operation side. So there is it's very, very costly to have a complex streaming application running, and probably some companies do not even need that. So that's why they don't adopt streaming.
Clear. Okay, let's do also a checkpoint on technology. No, we mentioned Spark Streaming. Now Flink and Kafka seems to be the standard de facto to approach streaming use case. Andrea Fonti, do you want to give an overview about the technology transition, newcomers in the market, new paradigms? What is your view?
Yeah, my view currently is that Flink is in some way dominating the streaming landscape. We have other tech stack we can employ. We can use Spark Streaming that has a notion of micro-batched streaming. We can use Kafka Connect, the Kafka Connect technology, so the paradigm where everything is based on Kafka. There are new brokers that are currently being adopted, like Apache Pulsar. We can also use serverless technologies or cloud vendor specific technologies like Kinesis Data Streams or Google PubSub. There are also managed offerings on Kafka that we can use. And also there is the notion of a streaming database. So databases that are able to maintain materialized views coming from data streams, so like building tables out of data streams, and that is, I think, stemming from stateful streaming. So having an internal state while streaming data, so for example performing streaming joins, is in a way like maintaining materialized view. So why can't we expose the internal state of the system like a table. So there are also efforts to build variable state backends, like there are projects based on Flink and that are building a database out of a streaming engine. So there is quite an overlap, and I think that what matters here is how you view those systems, because if you squint your eyes really hard, everything becomes a database in this landscape. For example, KSQLDB is something like that. Use topics like a write ahead log, so just replay a topic and rebuild a table once you start. So for me is that.
Good. I have seen also timely data flow as a new processing paradigm. This is employed by Materialize.io, that is doing materialized streams and tables. As you were saying, I see also Flink is going to offer a lot of these capabilities and features for a stateful streaming. Maybe on stateful streaming, because we are in the topic, what is your view on this? I always seen stateful streaming as very powerful and enabling capability to do analytics. Otherwise, with stateless streaming, it's not possible to run analytics in streaming. But on the other side, from an operation standpoint, managing this state is very hard. You need to be able to query the state. You need to be able to inspect this state. So in the past, we always approached the stateful streaming using an external database, not the embedded state backend provided by the streaming processing. Now maybe things are changing, are improving. What is your opinion on stateful streaming? Maybe still Andrea Fonti.
My opinion on stateful streaming is that it is extremely hard to do. In the past, we tended towards managing state on external database, because having an external database means we have a common query language, we have common data formats, data is not opaque, data is in a way inspectable and auditable, let me say. We had an experience in the past with Spark stateful streaming, where the stateful part, the data format of the state was opaque and an implementation detail of Spark. So it was extremely hard to manage. It was extremely hard to rescale, almost impossible. Spark would have fought with you to death to not let you rescale state. So once you take a decision about state, that is fixed in stone, unless you understand that there are non-functional requirements around what you are going to do. So for example, if you had a state with 5 fields, what happens when you add a new field and you load state that does not have that field? This is easier when you use an external database. For example, a relational database, just add a column, pick a default, and everything will work. When you're doing stateful streaming, you need to take care about the state schema evolution. You need also to take care about replaying events from another point in time. So if you want to replay events from 10 years ago, you also need code from 10 years ago to be able to deserialize the state and properly upgrade it. So it's difficult for me doing stateful streaming, because you need to always have available all the ingredients of the original processing and also a clear upgrade strategy. Now doing stateful streaming is kind of becoming easier, since there are a lot of technologies like Flink that are whose value proposition is around stateful streaming. So, for example, in Flink, rescaling the state when you want more parallelism is something that is automatic. A lot of these stateful streaming engines usually maintained the state in memory, so you needed a lot of memory, and memory that is proportional to the dataset you need to hold in state. Now, for example, with Flink, you can use the RocksDB state backend that is able to only load into memory what is actually accessed. So it's becoming a lot easier. So for me, having an external database while doing stateful streaming is like moving from a potentially distributed system to something that has a single point of failure at the center of every streaming pipelines that is the database. So the database where you store state should scale with your workloads. So it's like the processing power is not supplied by the streaming engine, but is mostly supplied by the state backend. That is something that is being queried a lot. So we want to shard this load as much as possible. So we want to manage state inside the streaming engine. But anyway, for me, the problem here is mostly non-functional requirement. What happens if we had a bug and we need to restore a previous state and replay all the events with updated code? This kind of...
So change management and let's say operations are still challenging in complex streaming environments. And talking about other challenges, Andrea Novara, which are the main challenges that you faced in implementing and designing streaming application from a technical standpoint?
I'd say monitoring is one of the hardest because the infrastructure is quite complex. You have to keep under control the broker infrastructure, all the applications that are processing data, both stateless and stateful, and as well also the user consumers that use that information to process them and take decisions. So having an overall monitoring infrastructure is quite complex and should be done properly. Otherwise, you are not seeing problems as they come, and you can intervene promptly to fix problems. So to me, the capturing metrics and taking everything under control is one of the hardest challenges. For example, if you have problems of data skews, if you have problem of overloaded processors that comes from data skews, for example, or outages in your infrastructure, and you then didn't intercept those problems promptly, you will have an increasing latency on specific partitions, and this will lead to not up-to-date data. And if you're using those data to take decisions, for example, in monitoring of an infrastructure, a utility or telco, or this kind of things, this will lead to missing action to fix problems or to even just report problems to people that should be able to decide what to do. So monitoring an streaming infrastructures means ensuring that anyone which is involved can have the information right in time to do their job.
Clear. And from a data quality standpoint, maybe Antonio, which are the challenges in applying data quality principles in streaming? Not that easy.
No, it's not yet. Also, the first, let's say, the cornerstone of data quality that we give it for granted right now is at least a schema. Well, that was a problem too when we started working with the streaming and Kafka, because Kafka does not limit you to. You cannot attach a schema to a topic natively, So everyone can push whatever they want to a topic, and the consumer can have trouble consuming that, because it can be JSON, it can be with a wrong column name or field name, it can be corrupted data, etc. So in the years, I would say now it's a de facto standard. We have a schema registry and formats, data formats and data encoding that help that part, mainly with the schema evolution, because again, as I was saying previously, this is an infinite stream of data that is being produced and consumed continuously. And so it's impossible to pick a point in time and say, okay, up to that point, I have this schema, and then I will have another schema. You need to build a system that is able to transition from one schema to another one in an easy way, operational easy way, and also it should be easy to develop too. Schema registry and Avro format help a lot with that, but obviously data quality is not just applying a schema to a data stream. It's a lot more. It's about also validation of the data, and it's possible to perform some validation, but with the current technology, you are going to do that after data is already pushed. So a common pattern is to have to apply data quality, or maybe we call that internally a contract guardian, is that you describe the properties you want from that topic. Maybe that number field is between some range or whatever, and you have a consumer that consumes the messages produced by someone else, and then we'll split those messages into two new topics, one with the records that are okay and respect the contract, and one with the ones that do not respect the contract. That works. It's kind of easy to understand and to implement, but it's costly, because you're paying double storage, more processing, and still it's quite limited, because in streaming, again, you end up in the complex event processing space every time you're trying to do anything that is limited by a window. So every time you are aggregating, you're opening the jar of the problems that come with the stateful streaming that we just discussed. So again, there's something we can do. And actually, a cool thing about Confluent, which is not available in open source Kafka, is that at least they can validate the schema before the schema of a message before it's actually successfully published to a topic, which is cool, because it's one less problem to care about. And I think this is a space that is going to be explored in the future. Also, I see a Red Panda, actually, which is Red Panda is a product that employs Kafka protocol, but it's a different implementation. So it's compatible with Kafka clients, but it's not Kafka. And they allow you to deploy functions inside your Red Panda cluster, which actually consume data and produce new data. So you have it all in the same system, which might be good or bad. It's up to you. There are pros and cons. But the nice thing is that it runs in their environment. So this is something it's very hard right now in Kafka to just deploy a function inside the Kafka cluster and to embed. And the next step to me is to embed that function into the broker logic. So to say, I'm able to redact some data before publishing, I'm able to validate it, which is what Confluent does. And I think this is something it's going to evolve in the future, because it's a lot like constraints into a database in the end. So definitely.
It seems to me more like stored procedures in a database that I don't like too much. I see also Pulsar is providing some capability to embed lambdas in the broker ecosystem. I see the value. I see also the limits in this probably. But talking about these kind of capabilities and data quality, in the past we spent a lot of time in ensuring the customer that the raw count in the replicated systems was exact, because we don't have the exactly ones. We want to have the assurance that all the rows and events have been processed, which are the common strategies to do this, because I remember exactly once, yes, it's guaranteed, but in a small portion of the whole journey of events, you typically need to guarantee the exactly ones from the source to the destination, not only at Kafka level. So how do we guarantee this usually?
So I will take this one, but guys, if you want to add something, just raise your hand. So I'd say in the past couple of years, we got to a point where we cannot implement exactly once, as Paolo said, because there are multiple systems involved, and distributed transactions are complex in a single system. Let's say you have two distributed systems and you want a transaction, a distributed transaction between two different systems. So let's say Kafka plus a table format, Kafka plus S3 or a database. That's practically impossible. So what we are doing right now is implementing every storage operation, let's say, as an idempotent one. So if you have at least one semantic on your event processing, so you can process the same event multiple times, but you have idempotent writes, then you are effectively once. This means the row count will be correct at the end of the day. And that's the way you can do it. There's a gotcha that obviously implementing that kind of idempotent writes, even in the face of duplicated events, is costly. It's not impossible, and depends a lot on the target storage system. So you need a system that supports that kind of writes, which is not common or is not cheap. So I was working on a project a couple of months ago about that. We were able to implement that using Iceberg, Kafka, and Spark structured streaming. And the hard part is that if you want to do idempotent write in Iceberg, every write is a join, and join are costly. So you need to find a way to make those joins more efficient. What I see is that the community is building storage systems that are built for that purpose, like Pymon, which is let's say a side project of Flink. It's a table format that keeps an LSM3 to simplify that kind of write, so idempotent writes. And it has its limitation. Also, Apache UDI, which has a very low adoption, is the only table format, all the table format, let's say, because Pymon is quite new, that that has that concept in mind from the beginning. I think that the hard part is that, but solutions are coming out, are actually already here in some cases, but again, they are quite specific. So you need to build your work platform with that idea in mind, which is constraining.
Andrea Fonti, do you want to say something on this?
Yeah, I have a take on this as well. For me, requiring exactly once in streaming systems should be not something we strive for. It is great, it will be great having that, but for me it's like an excuse to not reason about your workload. What is hard in guaranteeing idempotency is that there is no general way to do that. You need to be clever, you need to implement clever strategies, you need to understand the phenomenon you are handling, so the functional meaning of data, and preventing producer to produce wrong data on the broker, it's like not allocating for me the right responsibility in the right place. So centralizing everything and having exactly once for me is like producers are dumb, consumers are dumb. Let's do something that works in every scenario. I don't think that this, from an engineering standpoint of view, is a good way to move forward. I would like to distribute responsibility as much as possible. This will increase the complexity of the system, but you will get systems that properly understand data and properly handle that and also faster systems. Maybe what we are missing is a way to reason in a general way about idempotency, so like something that is the relational algebra of streaming data. I think we are missing that building block more than a system that can guarantee exactly once, but I think this is more of a philosophical take than a technical one.
Yeah. Good. Linked to this topic, the last question is how do we test this kind of system? Because we talked about the challenges in managing state evolution, change management, input load. How do we replicate input loads when we are doing integration testing? So how do we handle testing of streaming application? Andrea Fonti or
I have quite experience in load testing, so I usually strive for having load generators. Having load generators means emitting synthetic traffic that has the same shape and the same statistical properties as the input traffic. So the first thing you should do to properly implement that is understanding the traffic that you get. So for example, monitoring production traffic for a couple of months, understanding if there are trends, if there is some kind of seasonality, something like that. Develop load testers that are actually able to replay the traffic in a reproducible way. So if you launch your load tester, it should generate the same data all the time you run that, and also having an infrastructure where you can perform load testing. So what we usually do on our projects is having an environment where we can do exactly that. pre-populating topics, for example. Like in streaming, you can usually reason about time, but I think that is not the right way to do it. Since in Kafka you have a distributed commit log, you can replay that as much as you want. So preloading a topic, for example, and launching your streaming from the first offset in the topic is like replaying a scenario where you have infinite speed. Data is coming all at once, and that will give you, for example, the max throughput of your system. How fast are you able to absorb that load? So this is related to load testing, finding the sweet spot. Also, another thing that is usually needed is a functional way of replaying event sequences. Once you find a bug and you understand which kind of sequence triggered it, you should need a way to embed that sequence in a unit test, for example, and with that you get no regression tests. This is usually a challenge.
To solve out of order cases, right?
Yeah, I think that the out of order cases will happen anyway. So if you can design a system that does not rely on the ordering of events, that is a better way to move forward from an architectural standpoint of view. Because in streaming there are different ops, and those ops are usually controlled by different actors in an organization. So if you depend on an end-to-end notion of ordering, someone or something will break that notion someday. So at least if you have an architectural assumption like this stream will be always ordered, you have to monitor that, because the first time this will happen, you will not notice, you just rely on this guarantee. But every time there is an architectural assumption, I think you should have some kind of monitoring in your process that tells you, yeah, your assumption is not valid anymore. What do you want to do? Do you want to stop the stream or inform the consumers that are after you that you are outputting degraded data?
Yeah.
So there should be some exit strategies related to that. I usually strive to not depend on ordering at all, if I can.
And Andrea Novara, you had also some story, I know, about
it's a fun story. It's more about debugging a production application. We had a Kafka topic which was growing without applying retention policies. For those who don't know retention policies in Kafka, Kafka keeps data for a configurable amount of time. And when data goes out of that time window, it's automatically deleted. And that was not happening. And everything seemed to be configured properly. And after checking everything, we decided to check timestamps inside the messages because it's time related, the retention mechanism. And after checking all the messages, we discovered that some producer, one specific producer, which was using not production ready code, has emitted messages with timestamps in microsecond and not millisecond. So actually, that messages was located in the year 51,000 in the future, and so it was blocking the retention mechanism from deleting data. And so we decided to check the configuration of Kafka, and we switched it to use Kafka timestamps to calculate retention policies instead of sources timestamp. So we still had sources timestamp in the messages, but Kafka was adding its own messages from that moment on to govern retention policies. That was another point of monitoring in my experience that was very, very subtle to catch and created a lot of problems on the operational side.
Also good way to decouple from producer inefficiencies or bugs. Very good. I think we touched a lot of points: stateful streaming, change management, technical challenges. So I'm very happy. Very good discussion. I think it's clear that the streaming landscape is still complex, but it's moving fast, I guess. It's moving very fast. There are a lot of investments in this area, but challenges are still there to design and implement systems that are guaranteeing consistency, are handling scalability, managing the state for analytics. We didn't talk about security. Probably we need a full episode just to talk about security in streaming application. But yeah, this is the current state of streaming up to our vision and comprehension of the market. I'd like to thank our guests, so Andrea Fonti, Andrea Novara, Antonio Murgia, for their contribution, and stay tuned for the next episode of Data Architecture Elevator.